Hello, everyone. We're just getting started and letting people in from the lobby into the webinar. So thank you for joining us from wherever you are. Good morning, good afternoon, good evening, and good night, some of you, late in the evening. Let's just give folks another minute or two to join in before we get started. So thank you for your patience, and of course, we really appreciate you being with us. And before we get started, of course, here we are on August 18th and getting really excited about the upcoming IWCS Cable and Connectivity Industry Forum happening in Orlando, Florida, here in the USA in September. It's early this year. Normally we do it in October, but it's early because of rescheduling from COVID and any number of other things that are had us move the conference early. So things are coming up faster than normal, but we hope that you will come and participate. The program is absolutely outstanding. I mean, we're going to hear about some really visionary stuff, artificial intelligence and electrification and all the things that are going to be happening over the next 25 years, which it's exciting. It's also quite scary, but anyway, think about where we were 25 years ago, and that'll give you an idea on where we're headed 25 years from now. So that's all going to be talked about at the IWCS conference in Orlando. So again, we'll just wait a minute more. All right, why don't we go ahead and get started? There may be a few late folks joining us, but we can go ahead and get started. So again, welcome to today's IWCS webinar. My name is Dave Cadu, and I am honored to be the CEO and Director of IWCS. I'll be your moderator today, and for a few housekeeping items, I do want to mention, hopefully there'll be a number of questions that you have for Brian, but if you have those questions, please enter them in the chat function. You'll find the chat button either at the top or the bottom of your screen, and just enter your question and be sure to hit send. And we'll monitor that, and at the end of the presentation, I'll present those questions to Brian as time permits. Hopefully we'll have plenty of time to answer all of your questions. So again, use the chat function in writing, but as an attendee, you are part of a larger audience. So during the presentation, all participants will remain in listen-only mode. And again, as a reminder, this is being recorded for rebroadcast. We will post a recording of this presentation in case you want to share it or watch it again on our website. So it normally takes a week or so to get that all up and lined out. So feel free to go to our website and see it again. So again, the IWCS webinar series, it happens every month. It's hosted by the Cable and Connectivity Industry Forum. And today we welcome Brian Risch, who has been with us a number of times with excellent presentations over the years. Brian is the Materials Technology Manager for Prysmian Telecom in North America, located in North Carolina. Brian will be presenting his paper today on the impact of jacket configuration on temperature and strain sensing performance of optical fiber cables. And this paper was presented at the last IWCS conference in Providence, Rhode Island, as paper 4-4 if you have the proceedings and want to look it up in the archives. Dr. Risch is the Materials Technology Manager, as I mentioned, for Prysmian. He holds a bachelor's degree in physics from Carleton College, and a doctorate in materials science and engineering from Virginia Polytechnic Institute and State University. Brian has more than 30 years of experience in the study of structure property relationships in polymeric materials and materials reliability. Brian has over 20 years of experience in the fiber optic cable business. Prior to working for Prysmian, Brian also worked for Alcatel and Draka, specializing in cable materials and fundamental material reliability. Brian also has 6 years of experience at Hewlett-Packard, doing failure analysis engineering. So a lot of great experience in our industry, and we're very proud and appreciative of having Brian with us today. So thank you, Brian.
Yeah, thanks for the introduction, Dave. And I got to figure out how to. Is the minimized window showing on your screen? Is your picture on?
No, everything looks good.
Okay, good.
Looks fabulous.
Trying to figure out how to do that, but I think we're good to go.
I think we're good, yeah.
Thanks for the nice introduction. And I'm going to kind of go through the slides from an earlier presentation. And, you know, the work for this presentation was focused mainly on optical cables used for pipeline sensing, but there's some really interesting information that can be applied to other areas, including cable design, as well as cable testing. So, you know, it's a nice fundamental study, and it kind of goes beyond these sensing cables, which have been out for a couple of years, mainly deployed in pipeline sensing, which is a very important application. We're going to start off giving some introductory material, kind of explaining how the sensing technology works. It's kind of a little bit of a specialty application for optical fiber cables, but still very important in a growing market. We'll talk about some motivation behind the study and some of the technical challenges that we faced and why we wanted to get the data. It was a very complicated experiment to set up. It required coordination with our optoelectronic equipment vendors. So I'll talk a little bit about how we set up the experiments. A lot of work was put into that. A lot of people were involved with that. Then we'll talk about the results and some of the conclusions. To start off, we'll just talk a little bit about optical fiber sensing technology. Basically, the information, you know, in optical fibers is carried by light. So you can have your normal signal at a given wavelength, but there's also information in the light that's scattered. Scattering occurs in all optical fibers, and it's a normal process. These fibers that are typically used for sensing, it's a special selection, but the scattering behavior of these fibers is not dramatically greater than those of ordinary single mode fibers. So the primary scattering mechanisms present in optical fibers, we have Rayleigh scattering, which basically is occurring at the incident wavelength. This gives you a signal of both temperature and strain that's proportional to the scattering amplitude. So basically, as you put more stress on the fiber, whether it's thermal stress or mechanical stress, you'll see an increase in the Rayleigh scattering signal. There's also scattering information due to Raman scattering. The Raman scattering peak is shifted somewhat from the incident radiation peak, and it gives you a temperature signal, which is proportional to the scattering intensity. Today, we're going to be focusing on Brillouin scattering, which again, it is a shifted in wavelength from the incident light. And with the Brillouin scattering, you're primarily measuring in traditional equipment a shift in the Brillouin frequency, which is there's a characteristic shift that's associated with a fiber and some variation depending on frequency. But the Brillouin frequency or the Brillouin intensity can also have a function of temperature dependent, similar to the Raman scattering. And we'll talk a little bit about that in more detail today. Basically, from the sensing technology in the fibers, you can gain information due to the scattering from the time domain as well as a frequency domain. From the time domain information, due to the fact that light has a fixed propagation speed, you can determine the distance where there's an external stress applied to the optical fiber. So this allows you to, time resolved or spatially resolved information in the optical fiber, which is very useful to pinpoint an event. The frequency information tells you about the magnitude of the stress, whether it's temperature or strain. So what we have here is kind of an example of if we're putting an external stress on an optical fiber, we can see here is the Brillouin peak associated with that fiber as a function of length. And you can see at the location where the stress is located, we see a shift in the Brillouin peak. So this allows us to kind of determine both where an external stress occurs and the magnitude of the external stress. We can look at the impact of temperature as well with this kind of the diagram here. Here's an example of applying a thermal stress on an optical fiber and the Brillouin signal. So you can see where we've applied this thermal stress. We see there is a shift of the Brillouin frequency, which is a function of temperature, but there's also a slight shift in amplitude. What we can do is if we have two strains, one is a mechanical strain and one is a temperature strain, you can see the mechanical strain is really showing only a frequency shift. The temperature is showing both a frequency and an amplitude effect. So if we have an event that occurs in a place that includes both a temperature and a frequency response, we can deconvolute the results. So this is not available with all optoelectronics and data analysis softwares, but it's something we were investigating in this study. So the benefits of distributed sensing are many, so we'll go over some of them. First of all, the distributed sensing allows early detection of an adverse event. So basically, very early on in an event, you can determine, ground movement or leak detection. The old pipeline technology is they measured a pressure drop. So you could have actually a substantial leak in a pipeline if you're just monitoring pressure drop and not even detect it at all. So this allows a very early detection of leaks, or even before you get a leak, if somebody's digging in the area of a pipeline, you can detect that. It also allows a very high spatial resolution. We're going to give some examples of this that clearly show it, but clearly you can resolve it within a meter or so along, tens of kilometers of pipeline. It really makes the process of, mitigating issues very effective, and you can be done much more quickly. Another thing is you can kind of monitor the status. It's a function of time, so you can kind of see, okay, especially if you have seismic movement or ground settling, you can monitor the evolution of stress along a pipeline. Even if you don't have a critical event, you can kind of monitor problem areas and track them as a function of time. Share the data, save the data, compare before and after. It allows a lot of additional information. And basically, it allows you to look over the entire length continuously of the monitored pipeline. So it's not, isolated detectors such as cameras or something. You can get continual information over the length of the entire pipeline. So very useful, good application for pipelines, and it's pretty widely deployed, and we're seeing more and more deployment. So, how does the technology work for leak detection? Well, typically we have two types of pipelines. We have liquid pipelines, gas pipelines. In a liquid pipeline, generally the fluid within the pipeline is at a higher temperature than the soil around it, and liquids will tend to settle in the event of a leak. So an ideal cable location for liquid pipeline deployment is below the pipeline. And what would happen here in the event of a leak, the warmer fluid would come in contact with the cable. The cable would get warmed and we'd see the signal within the fibers. kind of the opposite thing happens in a gas pipeline due to the Joule-Thomson effect. There's typically a temperature decrease when you have a gas pipeline leak, and typically the gases will raise. So in this event, you'd want to deploy the sensing cable above the pipeline. In the event of a leak, you'd see a temperature increase in the cable, and you'd be able to monitor it with the fiber. So what are some of the requirements for pipeline leak detection? Well, first of all, from the slide, you can see that you want a cable that's suitable for direct burial. And typically, because they are direct buried and they're next to pipelines, you want pretty good, robust technical and mechanical performance. This may be demanding in some cases with regards to typical cable deployment, so you might want something even a little more robust. Large operational temperature range is really a good factor. We have deployments, all over the world for this type of application, in areas as far away as Siberia, in very cold environments, Canada, Alaska, Arizona. So all the potential environments need to be considered for the cables, and you can see a lot of variation in temperature along the length of a pipeline. A very important thing is the independent characterization of temperature and strain. I showed how these can be somewhat convoluted in the Brillouin signal, and how you can use, electronics to separate, and signal processing to separate out the signals, but our cable design allows additional ways to differentiate the signal from different fibers and different units within the cables, and I'll talk a little bit about that. A nice feature of the cable designs that we're going to be discussing is the capability to add optical fibers for telecommunication or other sensing or data technologies. So you might want to put things, you might want to have a communication network along your pipeline. You might want to have information on switches or electronics at pumping stations or valve stations. You might want to put monitoring cameras along there. So having the optical fiber technology along the pipeline link allows you to also have all these additional technologies for security and monitoring. What are some of the challenges that we're facing, right? So, I talked about direct burial. Obviously, it's important, and the motivation behind these dual armored jackets that I'll be discussing actually came from our customers. Our customers have seen these cable deploys, and they ask us, have you ever seen these cable deployed? Look at these optical fiber cables, compare them to the pipeline. There's going to be potentially boulders getting thrown in there and stuff. They wanted a very robust cable. So we had already offered this cable with, dielectric and a single jacket configuration, but our customer said, we want the most durable cable that you can make. Our concern was, well, if we make this, put extra armor and protection on the cable, it'll certainly have better protection, but what will that do to the sensing properties, especially for thermal sensing? So, the question is, what's the trade-off? And we had to quantify that. So that was kind of the motivation behind our study. So as I mentioned, in theory, we can do it. You can take some cables with different jackets and heat them up, but to do an actual experiment was pretty complicated, took a little work. First of all, we had to find the optoelectronic equipment. We've dealt with many partners in this industry with sensing, and Prysmian has some of its own sensing. But for this study, we worked with Leos, which is a Luna company, and they have a BOTDR. And basically, it does allow some additional signal processing with the new technology to kind of back out these frequency and amplitude signals that I talked about. For temperature monitoring, you can use both the frequency or amplitude measurements. The frequency is most typically used for Brillouin temperature sensing, but it is convoluted with any mechanical strain on the fibers. We can kind of work around this with cable designs, but if you get a second technology to help you out and improve things, The advantages of the frequency signal is it's very proven. It has the best temperature repeatability, the highest range, and the highest sensitivity. So that's kind of tried, it's proven, but there is additional information available from the amplitude. It does have more noise, lower range, but you can essentially greatly limit the strain crosstalk, which allows you more information. So more information is better, and this really doesn't require a change in the cable design. So let's look at the cable designs. All of these cables have essentially identical cores in them. The cores of the cables have loose tube elements where the fibers have a strain-free window. The strain-free window in these fibers goes up to about a 600-pound tensile loading of the cable in all cases, and we'll show some data to demonstrate that later. So that means that basically a temperature signal in these fibers, which there can be up to 12 per tube, will essentially not have any crosstalk with the strain signal, which is good because then you don't need the special data processing. We also have some tight buffered units which are coupled with the cable, and they're going to strain linearly and immediately with the cable strain. So these are strain sensing elements, and you can kind of change out the number of temperature and strain sensing and telecom fibers in the cable. But typically we will sell a 6-position cable. Taking this core, we looked at 3 different designs. We had the dielectric cable design, which essentially does not have any armored cable design with a single armor layer, and a dual armored cable design, which has an additional jacket and an additional armor layer. Typical cable weights and options available here are shown in the table. You can see that as you go, obviously with the higher jacket options, you increase the diameter and very substantially increase the cable weight, but this might be a trade-off if you want that extra protection. So let's look at each design one by one. The dielectric cable design, it has some certainly advantages for sensing, increased sensitivity to external stresses and temperature as well. The disadvantages are it's reduced resistance to crush and pressure. It's more prone to rodent attack. This design, if you can install it and it won't get damaged, it's probably going to give you your best sensitivity, best thermal response. You want a little more protection. If you've got an area where you have any rodents, that prairie dogs especially, you probably want at least an armored protection, and give you some crush resistance too if you're more concerned about less care and installation, rocky soil, stuff like that. This might be a good design for you. Disadvantages, putting that extra material in there may reduce sensitivity to mechanical stresses as well as temperature. Finally, we have our dual armored cable design. This is the most robust cable that we looked at. It's the biggest. So you have 2 jacket layers, 2 armor layers. So this gives you your superior crush and pressure resistance. It's the best in class. You get your best rodent resistance. You have 2 layers of armor for the rodent resistance. Also, the increased cable diameter helps you with the rodent resistance. And a lot of areas where pipelines are deployed, there's also a chance of rodent attack. So it's a very important consideration. The disadvantages are, when you have this increase, extra layer of armor, extra layer of jacket, you're probably going to have some substantial trade-off in response to stress as well as response to temperature sensitivity. So let's look at what we did. First of all, we had to manufacture the cables, so I kind of discussed how we did that. For the thermal excursion testing, what we did is we put sections of the cable with a suitable distance of cable and fiber to do measurements within a thermal chamber, and we connected outside of the chamber. We concatenated all the ends of the cable so we got a continuous length, so we could measure everything simultaneously. We also placed a length of bare optical fiber in the chamber. So the bare optical fiber will give us an almost immediate information about the actual and true temperature in the chamber and the variability from the top to the bottom of the chamber, because we're programming the chamber to ramp down in temperature at a controlled rate and a very rapid rate. So there is going to be some thermal lag in the chamber. So we need to deconvolute the thermal lag of the chamber from the different thermal lags of the cables. And basically, once we concatenated all the fibers and determined that they were all connected and worked together, we put in a 24-kilometer lead fiber. We did this in order to kind of make this less of a controlled laboratory experience and a better simulation of real world. Because in real world, your electronics are not going to be immediately adjacent to the fiber you're measuring. So this is kind of simulating an event that's many kilometers, 20 kilometers away from kind of a centralized sensing station and control station. So we started off, we double checked everything at room temperature, and then we equilibrated the cables in the chamber at 60 degrees C for 1 hour to make sure everything was at full equilibration. And then we ramped down to at 20-degree increments and then held for 1 hour for equilibration to kind of look at the response time and the decay time. And we did this from 60 to 40, 40 to 20, and 20 to minus 20. So we covered a wide temperature range because the thermal lag may vary somewhat as a function of temperature. We also did some mechanical testing, and we've given talks about the mechanical testing of these sensing cables, and the general behavior is, pretty similar to traditional loose tube cables, although these cables do include the coupled fiber elements, and we'll go over some of that data. But what we did in this case is we added a hot box, which was controlled at a temperature of 40 degrees C during the testing. So we deliberately introduced a thermal stress in combination with the mechanical stress to see how this could be deconvoluted. And as I showed you before, there's two ways that these signals can be separated. One is through the different elements, the strain-free elements and the strain sensing elements within the cable. And the second way of deconvoluting the information is through data analysis. So we can kind of look at how we did both of these. And again, we used a 24-kilometer lead-in fiber to simulate real-world measurements at a difference, especially because of the Brillouin amplitude shift that's proportional to temperature does have a little bit more noise with it. We wanted to ensure that it would still work at this distance. So now that we've gone over all the experimental setups, we can talk a little bit about the results. First of all, the general cable performance. I'm not going to go into this in great detail, but one thing I do want to point out is the typical installation load of the cable is 600 pounds. This is kind of typical for the industry. I'm going to show some test data above this rated cable load. And in some cases, you may have an accident or an adverse event, during the deployment of the cable. We've shown the cables will work above this, generally not, recommended for normal design, but also, is there linearity in performance? What does a performance look like above, the rated performance, especially for sensing? So we'll go into that information a little bit more. I'm going to go over this tensile strain behavior. I did say the cable was designed to have strain sensing elements, which strain linearly with the cable elongation. And you can see when we look at the actual data, yes, they do. So the cable's performing, as we've designed it. You can see there's a slight offset due to the stranding in the cable, but very good linearity. The loose tube fibers have a large strain-free window to nearly 600 pounds. And you can see, yep. So basically, if you're loading this cable, it loads typically below about 600 pounds. You should have an independent characterization of temperature from the loose tube elements and a characterization of strain. Remember, these fibers will still have a temperature signal associated with them, but you can subtract the shift from these fibers from those to get independent data. So that's how these cables are designed to work without any special data processing due to the Brillouin amplitude signal. We can look at a function of design, how the armor configuration might change the tensile strain behavior of the cable. So if we go from a single armor and add the extra armor layer, you get about a 10% improvement. It's not dramatic because the armor is corrugated, but there is more material to pull on. So you get, some difference in tensile performance. One thing I would like to show you, though, is we took two cables, one that was manufactured in 2015 and one that was manufactured in 2021. We did the same test, and you could see we get incredible repeatability of results, which is very, very good and very important for these sensing applications. Looking at the cable compression behavior, you see a little bit more of a difference between the different designs. You can see the basically what we have here is cable displacement as a function of crushing pressure. And of course, the dielectric cable shows the highest displacement as a function of crushing pressure being crushed between two plates. You get a pretty substantial improvement of about 20% when you add a single layer of armor, and you get about a 40% improvement in crush behavior when you have the dual armor. So that's pretty substantial, and that's kind of what motivated our customers to want this, beefier design. If we look in the cable tensile performance, we are hoping that if you measure the cable elongation, say with a strain gauge or an extensometer, that you get a good correlation between the Brillouin shift and the fiber. So this is really what is showing, which we obtained from tensile data. So we have the Brillouin shift, which is a frequency shift of the Brillouin peak as a function of cable strain. And you can see we have great linearity here. So that's good. That means everything's working properly, and it'll work as a good sensing element. If we take data measured on the same cable with a strain gauge attached to the cable and the Brillouin data from the fiber, you can see the data is, identical within the noise, and it's at a very low noise level. So again, that's very good news. So moving on, what if you add a hot box, right? And I think you should know the answer already, because you actually see an offset in the Brillouin peak as a function of temperature. So here's what kind of the raw data will show you for temperature. So if we look at the temperature sensing elements within the cable, you can see they're showing a Brillouin shift along the length of the fiber that's pretty uniform. But then in the areas that are in the hot box, you see a peak, and that's a 4-meter hot box. I mean, you can clearly resolve within a couple meters, and if you collect data for longer periods of time, you could get even better spatial resolution. So clearly you can see this hot box. And what does this do to our temperature analysis? So basically, if we take out the temperature data from the cable strain, we can actually accurately measure the cable strain within the cable, even with this temperature offset, using that data deconvolution strategy that we discussed before. So this kind of demonstrates that you can, electronically, from even with the strain sensing elements, which are subject to the strain, you can get the information from the temperature dependency. And what we have here at the bottom file is the strain sensing units, and what happens with them as a function of temperature. And if you take away the temperature signal using the data correction, you can see that you can get a nice linear strain response on the cable, even to strains above the rated cable strain. And I mentioned earlier that, yeah, we do have strain-free elements, so we would be able to deconvolute this data just based at lower strains below 600 pounds. You can clearly see that, oh yeah, there's this offset here of about 20 megahertz. Well, we can just subtract that from this data, and you could similarly get the linear response, but it loads above the rated cable load. You actually get some strain that you can't correct just doing a direct correction based on the information from the strain-free fibers. So there is some utility and added information possible through the data manipulation, which is very beneficial. And again, you can see here this offset due to the temperature raise of about 20 degrees C is about 20 megahertz here. And if you look here, it's about 20 megahertz here. So, it all makes sense. And if we look at the temperature sensing performance of all the cables, you can see the different designs at equilibrium, they're performing identically. So, some interesting data. We've shown some interesting data manipulation. We've shown there's a couple ways that you can deconvolute the temperature and strain signals in the cables. But what we really wanted to understand was, how does the jacket design impact the thermal performance? Do the cables still work for thermal sensing? So here's the data, and there's really a lot of data here. Basically, what this is showing you is the actual temperatures being measured during our study. So this is equilibrium. Here's the ramp, equilibrium, ramp, and then we go back up. So we went up and down in temperature. The black data is the bare fiber. So really that's telling you the thermal response of the chamber. Of course, you turn the temperature in the chamber, it doesn't respond instantaneously. We tried to use a small chamber to maximize the speed of response, but even the chamber itself. But you can see there is a measurable lag. The blue data is the non-armored cable. The red data is the single armored, and the yellow is the dual armored. And when we first looked at data, said really there wasn't much of a difference. We were very surprised that everything was so close together. What we're going to do is blow it up a little bit, and you can see that there's really no difference between the single armor and the non-armored, and actually the single armor cable appears to be a little bit better. And we thought about this a little bit, and if you think about it, well, you actually have a thermal conductor in there, so that the steel armor has pretty good thermal conductivity. So really, it's not much of a trade-off. It's almost equivalent. Of course, with the dual armored jacket, you have an extra layer of plastic, so you do see a little bit of a delay. But really, the cable is still doing the job. There's a slight thermal lag, and we can now quantify this thermal lag. So we were very a little bit surprised by the results, that the performance was impacted at such a low level, and we were very pleased that the cables were still working well. And we were able to quantify kind of the characteristic decay times for the different armors relative to the optical fiber. So these are the kind of decay times with a 20 degree C nearly instantaneous temperature lag. So you can see we're going from between 9 and 6 minutes to between 14 and 16 minutes. Again, overall, the single armor appeared to have the most rapid performance. So, we really learned something from this, and it provided us information that can be used by customers. But typically in a pipeline leak scenario, the penalty that you're going from, maybe losing about 10 minutes in the, response time is pretty minimal. And for most applications, the customers are going to deem this as certainly acceptable. And if you can determine a leak within 15 minutes, that's really a pretty good result. So we can move on to the conclusions here. So we saw about a 20% improvement in compression resistance, with one armor layer on a pipeline sensing cable, and about 40% improvement with dual armored. You might get a slightly greater benefit for puncture resistance and things like that. We haven't exactly quantified those. We saw a real surprising result, which was very positive, is we really didn't see any thermal lag with a single armor jacket, which says that, yeah, that's probably for any buried application, you're really not losing too much in going with it. So that's typically what we're going to recommend, as we would for direct buried cables deployed for other applications. This is probably due, almost certainly due to the conductive property of the armor. And we saw the maximum difference in thermal lag between the dual armored cables relative to non-armored cables was 11 minutes. So this, probably indicates that, hey, having this dual armored cable design was probably a good idea. We can't claim 100% credit for it. It was something that was suggested, asked for by our customers, but it looks like it is a good idea. And we've also demonstrated an additional method besides cable design of deconvoluting the Brillouin strain and temperature signals from a single fiber. And we've also demonstrated it outside of a laboratory to a practical link distance in excess of 20 kilometers. So I'm concluding the talk now, and I think we can move on to the questions.
Thank you very much, Brian. Again, very clear and very interesting work. Again, it was very well received in the conference last year, and again today, very, very helpful. And one question is, you did show some data of comparing the testing, 6 years apart. I think it was like 2015 to 2021. And I think it was for crush, but it could be, for strain and other things.
Yeah, that was.
What's that tell you about the life of these cables installation? I don't know if that affects warranties or whatever, but does that kind of tell you, say, hey, you'll achieve better longevity of this cable?
Dave, you're leading into future talks. We've given several talks on the lifetime. On these particular cables, the materials and the designs, we've certified, already, a lifetime in excess of 30 years. And, we're continuing to do some modeling. I'm going to give a paper on fiber lifetime. It's something I work on, but easily the lifetime is 30 years. These are highly stabilized materials, and typically we're very conservative. I do a lot of work in that area, so I always ensure everything's properly stabilized and formulated, but at least 30 years. So well after I'm retired, I can feel these cables be working properly. But I do want to clarify the data that I showed that was from several years apart. That wasn't the same cable. Those were completely different production runs, but they were produced 7 years apart. So the process variability and the performance of different cables is very repeatable in the process. So, you have to have a reliable product, but you also have to have a reliable process.
And those comments apply to all three cable types, the different armoring configurations.
Yeah, the materials are essentially the same in them, and they're highly stabilized.
Excellent. What is the typical temperature range specification for bare fiber used in sensing cables?
The fiber itself will typically work from minus 60 up to 85. Cables, typically for this cable design, we will typically certify it from minus 50 to 80 for the cable performance. Again, I'll be giving a talk on fiber reliability in a couple weeks, and this kind of shows the range of fiber temperatures. Looking at long-term aging, the fiber will function for short periods of time. Well beyond on a high temperature range, it can go. You can essentially pyrolyze the fiber. It'll still work. It's just you lose that protection. But the rated temperature easily up to 80 C, and typically as low as minus 50. The fiber can go a little bit above and beyond depending on the requirements.
Great. Are the buffer tubes gel filled or are they dry?
Both options are offered. We had a discussion a few years ago in one of our papers talking about the trade-offs between the gel filled and the gel-free tubes, you don't see a huge difference between the two.
Okay, good. Along with the temperature range question, what kind of temperature resolution can you get with this technology? You know, assuming that we are using non-armored cables.
Yeah, that's a good question. The temperature resolution, it can be below, 1 degree C. The resolution of any signal is a function of how long you're collecting data. So the longer you collect data, the more you can do data processing and eliminate noise.
Yeah. And are you using standard OSP PE jacketing materials?
Yes, in these cables we used standard polyethylene jacket compounds, but these cables, of course, you could put in if you needed a chemical resistant jacket or something like that. You could, I kind of demonstrated that you could change the jacket configuration. You could also put on a flame retardant jacket if it's needed, a chemical resistant jacket. These cables, basically the technology is around how the core is designed, and it'll work with other jacket configurations.
Good. What is the pitch of stranded elements in the cable, and what is the typical attenuation of tight buffer strain sensing fibers at 1500 nanometers? That's a detailed question. I'm not sure how much you can answer.
I can't give you the stranding pitch, right. And in terms of the tight buffered attenuation, it'd be a function of wavelength. I'd probably need to grab a data sheet on that to give you the right answer, but it's typical industry standards for tight buffered attenuation. So it wouldn't be anything different than what we'd offer, and it is something available on our online data sheets.
And again, I'm not sure if it's in your purview or not, just a request for sourcing, but I have a need for DTS testing using an MM50/125 GI fiber cable. I'm having trouble finding a company to rent a DTS system. Most are SM. Do you know of any companies there that provide an system?
I think you can reach out and I can help you out.
Okay, yeah, that's the appropriate way to do that. And I will.
Yeah, I think
share
that's something
Brian's...
that Prysmian offers some technology, but there's a number of folks out there. So depending on what you're looking for, I could help out on that.
Right. Stay tuned. I'll provide you Brian's contact points in just a second when we finish the Q&As. We just have a few more, Brian. What was the excess fiber length of the buffer tubes when you were doing the test?
That's another thing. It's kind of a proprietary design, okay. But you could probably do the math if you know the size of the fibers and the tube dimensions and the strain window.
Right.
Obviously, there was excess fiber length though, because the strain window.
Right. What is there any issues or differentials between the different fiber types?
Yeah, that's a good point. The fibers that perform the best, you can get any fibers in here. It gets a little complicated for Brillouin scattering. So in terms of the fiber design you want to choose, you want to have a single strong Brillouin peak. You want to have fairly good Brillouin gain. So fiber design, there's different fiber manufacturing process. Some will give you kind of a main peak and a side peak, which you can use those for Brillouin sensing. Some give you like a strong double peak, which adds noise to the data. So the fiber selection is important, and we have a special process variant. We've characterized all the process variants that are available to us, and we use a specific process variant that's optimized for these fibers that has a strong Brillouin peak. Typically, bend-in sensitive fibers are better because you have less noise with them. And consistent Brillouin shift. So you really don't want to mix fiber types, because each fiber, if it has a different process, it'll have a different Brillouin shift. You can kind of factor that out. If you get baseline characterization of the cable, it makes it more difficult. So fiber selection is very important. And typically, we will take orders for this cable with any fiber type if our customers request it, but we'll typically recommend that we use a specific sensing fiber type, which has been, has the right kind of a scattering performance. And I mean, that's a talk all into itself on fiber selection and fiber characterization. There is literature out there from Prysmian and others, but it's a very important consideration and quite complicated. I can't answer it completely in 5 minutes, but if you're going to buy a cable, that is something that it's important to specify what type of fiber, and you don't want it to be changing.
Right. I know you've talked about different types of jackets and the jackets that you used, but does the materials choice for the cable jacket have an effect on the sensing accuracy and the lag?
Well, yeah, I mean, in terms of the jacket design, you could impact, in terms of, you can look at different materials depending on filler level and things like that, even jacket thickness. It can have some sensitivity, but I think looking at the dual jacket, that's a very extreme difference. And, you probably aren't going to see more of a difference than what you see in the dual jacket, but you can probably see a measurable difference. Say if you go to something like a PVC jacket or something like that, or LSCH, because you have the impact of the filler there. So you'd probably see a measurable difference if you go to one of those materials, but not to the extent that we've shown, putting on another layer of armor and a complete other layer of jacket.
Right. Well, Brian, we really appreciate the perspectives and obviously the hard work that went into evaluating these cable types. And to our audience today, thank you so much for the engaged questions. Very, very good questions, and we thank you for that. Please note the contact points now being shown.
And please,
yep.
Dave, I prefer email, not phone.
That makes perfect sense. So with special request, if you want to reach out to Brian, and he does respond very well to email. So we appreciate you using that mode. But each of these webinars are recorded and will be archived on our IWCS.org website. So it normally takes a week or so, as I mentioned, to get them up. The IWCS webinar series is presented each month. We'll be skipping next month because of our conference taking place in Orlando. So that's exciting, but we'll reconvene the technical paper webinar events on Friday, October the 20th at 10:30 a.m. Eastern USA time. We try to be consistent with that third Friday in the month for our technical webinars. There are several other webinars that will be announced for special topics and some company specific issues. So before we conclude, I think Becky, we've finished all the questions. I didn't see any more questions for Brian.
Yes, I think we covered the questions. Thank you.
All right, perfect. Thank you. All right, so it's important that we all recognize and thank our IWCS partner sponsors. They greatly contribute to the success of the Cable and Connectivity Industry Forum with their strong leadership, their contributions technically, with the innovations, but clearly their generosity and financial support. And we would not be able to bring these important innovations and information to you and our global technology community. So again, thank you to these leading suppliers in our industry for your support. And that includes, of course, Prysmian and Brian Risch. So again, thank you for that. I do want to remind you that rapidly approaching is our IWCS 2023 Cable and Connectivity Industry Forum. Please take a look at the program, the final program has just been brought together. It will be posted here shortly. You'll be receiving information very quickly and links to the actual program. It contains some amazing things. Our team is really proud of what we've been able to pull together for you. So we hope that you will be able to get to Orlando. It's a nice time of year down there, and maybe you can have some fun too and visit our friends Mickey and Minnie Mouse. But at the same time, we would love to see you and participate in the program. So again, that wraps up today. Again, our next webinar, it will be in October. But again, keep visiting our website and monitoring our blasts to get updates on future activities. So again, have a great weekend. Thank you. Have a good rest of your day, and we'll see you next time. Thank you.